The next algebraic operation with matrices that we need to explore is that of the transpose of a matrix. So, here we are going to let A be some m by n matrix. Then the transpose of matrix A is an n by m matrix whose columns are formed by the corresponding rows of matrix A. And we denote the transpose of matrix A as A, T. So in other words, what we have here is that the rows of matrix A are equal to the columns of A transpose. And the columns of matrix A are equal to the rows of A transpose. So we can see here that we are interchanging the rows and columns of matrix A to attain A transpose, or the transpose of matrix A. So another way to think about this is in terms of the ith jth entry. So we can say that the ith jth entry of matrix A is equal to the jth ith entry of the transpose of A. So again, we're seeing here we're interchanging the rows and columns of matrix A to attain the transpose of matrix A. So to better help us appreciate this matrix operation, let's explore the following example. Here we are asked to find the transpose of given matrix A. So before we get started, let's quickly recall what we have discovered based off of our definition. So we know by definition that the rows of matrix A are equal to the columns of A transpose. And we also know from definition that the columns of matrix A are equal to the rows of the transpose of matrix A. So let's use this definition to help us find the transpose of our given matrix. So we have matrix A, and this is defined as Y-A-N-K-O, and the second row is W-S-K-A-S. Now, before we go ahead and even define A transpose, let's make a couple of observations. So the first thing I want us to observe is the size of matrix A. We can see here that matrix A is a 2 by 5 matrix. So, since we're interchanging the rows and columns of matrix A to attain the transpose of matrix A, without mapping anything, we automatically know that the transpose will be a 5 by 2 matrix. Now, to attain the transpose of matrix A, we want to begin by taking the first row of matrix A, and we are going to map this to the first column of the transpose. So in other words, that first row becomes the first column. We have Y-A-N-K-O. So there is the first column of the transpose of matrix A. And now we want to do the same thing with the second row of matrix A. We are going to take the second row and map this to the second column of the transpose. So the second column will read W-S-K-A-S. And that's it. This is our beautiful final answer for the transpose of matrix A. Now, I want you to keep in mind that this is not an exclusive way to find the transpose of matrix A. Again, if we start by thinking about matrix A, which is Y-A-N-K-O, W-S-K-A-S, instead of mapping each row to the columns, we could have alternatively mapped each column to a corresponding row. So in other words, we could have started with the first column of matrix A and mapped this to the first row of the transpose. So we could say the first row of A transpose is going to be Y, W. And we could continue right along with this. We could say, okay, well, let's take the second column of matrix A and we'll map this to the second row of the transpose. So the second row of the transpose is AS. And one more for good luck here. We could take the third column of matrix A and we can map this to the third row of the transpose. So the third row of a transpose is NK. And the remaining terms we have KAOS. So how you map is up to you, but you'll attain the same answer regardless.